As a new era of fast 3D printers emerges, we witness a surge in proprietary components and designs. Yet, there are those who remain steadfast in their desire to build one from the ground up, with hopes of keeping the spirit of rep-rap alive and thriving. The very same design philosophy that started all of 3D printing, do-it-yourself self-replicating printers.
With a budget of just $300, I was on a mission to build a very fast 3D printer, a do-it-yourself Bambulabs killer.
Join me in my journey as I build a CoreXY 3D printer from scratch, a 3D printer tutorial with a never-before-seen welded steel frame approach made from home construction materials, things I found from the flea market, and a bunch of spare parts that you might already have lying around.
Let's see if I did succeed, or did I go over budget.
My journey began when I went to a nearby hardware construction store as I bought some lumber supplies for building another steel table. From where I come from, $4 would get you 6 meters of 1 by 1 inch steel tubulars. It got me thinking, I haven't seen a single Voron printer or any 3D printer, to be frank, that has been built upon a steel frame. If I were to do so, I'd save hundreds of dollars for building one of those next generation of fast 3D printers by replacing the traditional aluminum profiles they are built upon. And me being the nerd I am, I always doodle on my notebook during my free time. How much steel would I need to build one of those fast CoreXY 3D printers? 5.24 meters! That is within an astonishingly low budget of $4. Cheaper than a burger at McDonald's. This project got me so excited I skipped all the CAD work and just straight up ditched my plans on building that welded table and just started cutting all the metal based on my doodle. I guess I'm building a 3D printer now. This is one of those freestyle projects of mine that would probably get my engineering degree revoked. I don't have a proper welding table with me as of the moment, so I had to make the most of what I got. I have this homemade workbench, and I did grab some sacrificial pieces of wood so I could have a relatively flat surface to weld on. I eventually resorted to using clamps to fasten the tubulars on the table, and a 45-90 triangle I used back when I was in uni for ensuring I get close to 90 degrees on my weld angles. This is my first time using a MIG welder, as I just got this Harbor Freight Philippine equivalent to replace my old arc welder. So please forgive me for my horrendous welds. I am an electronics engineer and this is not my forte. If you're going to ask me why I'm welding it peg by peg and not use all the magnetic clamps I have, that's because from experience back in the pandemic when I used to build lots of tables here at home, I get better 90-degree angles with a triangle instead of using all those magnetic clamps. In Filipino we say paghinang ng skwala, which closely translates to be able to weld at a perfect 90-degree angle. And that's what I tried to do. My friend suggested me the slow and painstaking process of using the triangle 1 by 1 peg by peg to help give me some sanity whenever the welds tend to warp the steel. And whenever it does, I give it a little nudge and it's back in place and I continue to weld even more. The main goal here is simple, to be able to build a perfectly cubed frame. Well, I mean, technically it's a rectangular prism, but you get a picture. Don't be scared, it does not have to be perfect. In 3D printing, we have a firmware, and that firmware can compensate for that error or that three-dimensional skew error to an extent through calibration. In my specific design, you'll eventually find out why the bottom does not have to be extremely precise, unlike the top frame and the spine. My MIG welds eventually got a tad better, but they're still nowhere near perfect, so I got my angle grinder to smoothen the surface to save the day. I had to add a spine for my gantry's Z-axis by cutting my remaining scraps of steel tubular to form a 1 by 2 inch backbone instead of buying another set of steel with a different dimension. I got a little lazy and dots of weld would do. I brought it to my cutoff tool to cut it to a specific length that would fit in my frame. And that's perfect. I then grabbed the ruler to get the midpoint of the top frame and marked it with a Sharpie. And also a quick tip, a T-square would help you a lot in the Z alignment. Use it to translate the marking from the top frame to the bottom frame to keep the Z-axis spine perpendicular to the top XY plane frame. This was done because I was an assumption that the frame is nowhere near perfect. I don't usually weld, I only do it when I need it. I'd be more than happy to hear some feedback or comments on how I can make them better, as it might help others in the comment section as well. There's actually a saying, when your welding sucks, let the angle grinder save the day. And that's what pretty much happened to me. Overall, I was quite happy with the outcome. It wasn't perfect, but it was better than I expected. Post-measurement showed me that the errors are workable and I eventually came up with ways on how to work around that. This isn't my first 3D printer build, and upon seeing the frame, I was quite optimistic with what the rigidity of this thing can bring me. This video is not sponsored by eGizmo. However, I would love to share my favorite mechatronics store here in Manila. I went here specifically to look for linear rails for my 3D printer sliders. These things are extra rigid and are relatively light compared to roller assemblies. They are often found in high-precision industrial machineries in assembly lines or perhaps in CNCs as well. In this shop, they do sell them for around $10 a kilo, and that's more than enough to get me 3 THK branded linear rails for my 3D printer's XY gantry. As for my Z-axis, I'm going with a linear actuator. But what really caught my attention was this Yamaha servo-based actuator. As much as I would love to use this for my printer, I have no idea if Marlin or Clipper has native support for the drivers this thing comes with. So I went with this. It's a ball screw linear actuator without a servo. Luckily, this is a lot cheaper. However, I would have to make a custom faceplate for it to work with NEMA 17 motors. At $90, ironically, it's going to be the most expensive component in my printer. It was a luxury purchase, and it was only justified to further simplify the design and build process of the printer. Upon checkout, they do some slight restoration on the linear rails. Today was indeed a good day. After I drove back home, I continued building the printer. I grabbed one of those linear rails. The ones available were a tad longer than what I needed, so I'm going to cut the steel rails. If your carriage does come with guards, you can just simply slide the rails off the carriage. I proceeded by marking the measurements of my cuts. Then eventually I brought it outside to my cutoff tool for cutting my linear rails. Quick disclaimer, this would remove the rust coating at the ends of the rails. You also might have to file the edges for the carriage to slide back in smoothly. As for the excess rails, I'm going to save the scraps for a future Voron Zero build. For mounting the rails, I first drew a scratch guide using a caliper and a marker. I have plans on giving this a heated chamber, so the carriages must be within the bounds of the frame as so not to protrude with the side panels. After marking the holes, you can translate your measurements to the other side using a T-square. With the assumption that my frame isn't perfect, to get both rails aligned parallel to each other, I used a T-square, a ruler, and some clamps. If the edges don't match, loosen that clamp and slightly move your ruler until they have equal lengths from the other end. After that, you can finally write the guide for the parallel line and the holes. Before you drill, please do use a punch tool so that the bits won't slip during the drilling process. I'm going to use M3 bolts, however, I wouldn't pair them with nuts. Instead, I'll be using my hand tap set for tapping threads so that my bolts would fasten directly to my frame. If you are one silly person, please don't force thread a bolt directly to steel without using taps. It wouldn't work. I was once that silly guy. Same thing for the extruder brackets. Mark, punch, drill, and tap. And yes, the tap works with the drill if you are lazy. It also applies to the front pulley brackets as well. Silly me, no marker would fit the hole, and luckily I had a failed aborted print of this bracket which I used as a stencil. Next would be the holes of the linear actuator for the Z-axis. Just find the midpoint of the frame and the actuator before marking the holes. Same thing applies, but this was a bit trickier since I would sometimes have to fit my entire head within the frame to see the marks properly. By now you probably know why I didn't pre-drill this with my drill press before welding. Mostly due to the post-weld compensation for the measurements. You have the freedom to choose where to mount your 3D printer's controller board. I decided to mount mine at the back spine. And that's pretty much how you drill threaded M3 holes on the frame for most of the components. I did miss some of the holes and you'll eventually see them later. The following morning, I spray painted the frame with a can of primer gray spray paint. It does help a bit with the chipping problem of directly painting your colored can of choice. I decided to give it a matte black finish as it was my favorite monotonic theme for most of my DIY machines. While I wait for the paint to dry, I continued with some other things, such as modifying that ball screw linear actuator I got earlier. The chunkiest linear rail with a ball screw in the middle I have ever touched. And just what I suspected. An NEMA 17 motor won't fit in the screw mounts of that actuator. So I had to add a coupler and that custom faceplate I was saying. I 3D modeled and 3D printed it, then added some heated inserts. It took a little courage from seeing it from the shop down to implementing that improv. I was then faced with another problem from that adaptation. It created an unwanted incline from my frame. Instead of using lame washers for elevating it, I grabbed a rotting flat bar and put my old scraps to good use as chunky spacers. I had to use 2 strips to make a proper spacer for this. That steel might be a bit too thick for my cordless drill. I guess this is a job for the drill press. If you don't have one, you can either decide to ruin a bunch of good bits with a cordless drill or just simply use a bunch of washers if you feel lazy as of the moment. Be careful of the metal shavings, and JC, please do forgive me for ruining your pasalubong. And that's how I made 2 copies of those flat bar spacers for my Z-axis. The paint has dried and I can finally mount my other components. It doesn't have to be in any specific order, but I did start by mounting the Z-axis actuator on the frame. Some of my video files got lost and I won't be able to show you how I welded some flat bars to form this cantilever bracket for my heat bed and linear actuator. I also messed up the distance between the holes, so I was forced to add another pair, got lazy, and just mounted 2 bolts to fasten it. Regardless, it's still exceptionally rigid and looks very minimal. I had a spare Ender 3 heat bed lying around, so that's what I'm going to use for this build. I also had to solder some wires to the heating element and the thermistor. The heat bed being my spare also came with springs and bolts. The process for this one is pretty standard and it's just like assembling any other 3D printer. And then let's install the knobs it came with. Turn it all the way up until you can no longer screw it. This is where I get custom cut Ender 3 size glass beds here in Las Piñas for $1. Call me old fashioned, but I still prefer to use glass beds up to this day. Rinse the glass with water. As for adding extra layer adhesion for prints, this is my favorite can of hairspray since 2015 for 3D printing. I'd usually reapply a layer every 6 months, and the key to longevity is a day of curing under the sun. Once the layer has dried, you can finally put it on top of your heat bed. To fasten it, you can buy 3D printing bed clips, or if you want something much easier to find, the classic butterfly clips would also do. I do prefer the bed clips as they consume less usable print area compared to the butterfly clips, but that's pretty much up to you. This is most of the plastic components needed for the build, the perfect example of a 3D printer replicating itself to build another DIY 3D printer. The first ABS plastic that we're going to mount are the stepper motor brackets. I designed them to be mounted by 3 bolts, 1 on top and 2 from the side. Once done, you can install a stepper motor on that bracket. The motors that I'm using are $4 NEMA 17 48mm steppers from Circuit Rocks. Rated at 1.8 amps each, it offers good torque for budget CoreXY builds. Sadly, I am using the classic dual gear drive Bowden extruder for my assembly, since I had a few of them lying around. As much as I wanted to go direct drive and use an orbiter, my current setup is cheaper, lighter on the print head, but comes at the expense of print quality. Moving on to the XY joints, force threading screws directly on plastic is a bad idea. The least I would do is embed some threaded heat set inserts on my plastic. A regular soldering iron tip would do, but I prefer these non-tapered ones as they don't lock onto the threads. Just some quality of life accessories for my do-it-yourself Faco 907 iron. I printed them on ABS, so 270 degrees would do. You'll need 4 16-tooth idler pulleys and 2 smooth idler pulleys. I have the M3 variant, so I grabbed some M3 washers and some recycled M3 screws from my box. Be sure to add a washer in between the pulley to elevate the bearing from the plastic surface. Then screw in your M3 bolt. This one's for the left and this one's for the right. I have plans for revising this in the future, but this would do for now. As much as I wanted to use a 1/2-inch tubular for the X-beam, I still had some excess 2020 aluminum profile left, so I'll use that instead. Measure the distance between the dual Y carriage and cut your X-beam of the same length from your measurement. The same length with your last linear rail. My X-beam assembly included the profile, the rail, and 5 M3 T-slot nuts with bolts spread evenly across the beam. I recommend the chunky nuts as they hold better than the slim ones. Installation is simple. Partially screw in your nuts with the rail, then slide in the aluminum profile. I also want to hear your thoughts if the profile was necessary and if I could just make an XY bracket that screws in directly to the rails for a lighter assembly. I don't know. Anyway, to install the carriage back to the rail, just simply use your thumb as a guide and slide it back in place. Moving on, slide in the right and left XY brackets to your X-beam. Don't tighten them completely just yet because we still have to screw them on the dual Y carriages. Adding some washers would help as long as you have ones that are tiny enough not to touch the pulleys. Then again, don't tighten everything just yet because we still have to align them. Your X-beam needs to touch the frame on both ends before doing so. If it does, you can tighten your X-beam. For the slight parallel alignment, slightly loosen your Y rails and abruptly slide the X-beam back and forth until you barely feel any resistance left. If so, fully tighten your rails once more. Your X-beam should glide smoothly like butter. Also, refilling the grease on your carriages might help. Here's how you assemble the front pulley bracket pair. Grab two 16-toothed idler pulleys, 2 washers, and a long M3 screw. Add a washer on top, partially insert the screw, slide in one pulley, then add a washer after it, and add the final pulley. Use your screwdriver to force thread your screw on the plastic. Do the same for the other pair, then install them on the frame. The assembly should now look like this. Both front pulleys should be in line with the frame. A quick sanity check with the leveling. Even without tramming the bed and springs, I was quite happy with how level the assembly was. Here's my 3D printed design for my printhead. It's quite simple and light. This one screws on to the X carriage, and I designed this one to go with a V6 Hotend set or a Bambulabs Volcano CHC. The aluminum bracket screws in like this. For the heatsink cooling fan, I'm using a 3010. The wires are routed on the back, so you might have to unclip them from the fan. I then screwed them in place with just 2 M3 nuts for weight saving. I then mounted the V6 Hotend in place. As for my part cooling fan, I'm using the infamous 4010 blower. The same thing applies to the wires. You might have to unclip them as well and screw them in place. For this build, the X Endstop limit switch is installed on the printhead carriage with wires soldered to the common and normally open pins. A zip tie would help with the cable management. For the short wires, I extended them with a flat cord to a length enough to reach the controller. Oh yeah, also please do use heat shrinks. For the severed 2-pin JSTs, set them aside as you can use them once more. A quick segue, this is the Mark II, my first CoreXY 3D printer build before the Mark III shown in this video. On this one, I did add a bed leveling sensor and used the Volcano V6 Hotend. Since I have a new printhead design for the Mark III, I'm going to copy that to my Mark II and also upgrade the V6 with a 120-watt Bambulabs Volcano CHC clone. To top that off, I'm going to use this 0.6 Volcano CHT nozzle for faster prints. With a bed leveling sensor, there are more wires to manage. It made me want to go the CAN bus route, but I had to stick to my budget. Back to the Mark III, I printed this nice cover for my printhead. Maybe someday I'll add some magnets to make it a quick detach. This is my old design where the wires go through it. Please don't judge me for the accessibility. But anyway, grab some screws, whatever screw fits, and screw that in place. Adding a jumbo heat shrink would also help reduce the strain on the wires. This is a nasty Bowden setup. Luckily, I have a box of PTFE tube spares back when my CR10 had a Bowden setup. I went with the blue Capricorns as they are better in terms of reducing internal sag. Move your printhead as far away from the extruder and cut your PTFE tube to the shortest possible length with the least amount of bend or strain. I had these old nylon cable sleeves from my CR10 when I modded it heavily back in 2017. I said, why not reuse them? So I did. They're kinda pretty. I like how the printhead came out to be. We're not done just yet because we still have to add a fan duct. 4010s aren't as bad as they call it to be. It's just most design and use highly constrictive duct designs the 4010 can't handle. So I made my own. And the printhead is finally done. And just like any other 3D printer, I'm using the standard GT2 timing belt for my CoreXY build. Also, print 4 of these belt clips and grab some zip ties. I then installed an inverted 20-toothed pulley on the left stepper motor and another one on the right pointing upwards. Move the printhead to the center of the gantry as we will be installing the lower belt loop. Grab your timing belt, insert the belt clip, and insert it to the lower left slot of the printhead. Fasten the clip inwards, then grab some zip ties to prevent the excess ends of the belt from dangling. Route the belt on the left XY bracket's front pulley, then around the left stepper motor, all the way through the front left pulley, to the right pulley, back to the XY bracket's tooth pulley, and finally back to the printhead's lower right belt slot. As for the top belt loop, everything is similar except that the path is mirrored. You can use this similar reference design from RepRap's website. Here's how I implemented my adjustable end stops. The Y end stop is mounted on the rear frame, pushing against the X beam, while my X end stop is mounted on the printhead itself, all configured as normally open switches. For my Z end stop, while I could have used another limit switch, I opted to use the Savage inductive proximity sensor for higher precision and reliability. It's wired the same way except I had to power it. I used 10mm standoffs for my 3D printer's controller board for elevation. For this build, I chose to use the well-known silent 32-bit controller board upgrade for 3D printers. the Big Tree Tech SKR Mini E3 V3. It has excellent support for firmwares and has a big community online. While this is not a popular choice for CoreXY builds, this is more than enough for my low-budget build. The elevation was done to prevent the PCB traces from touching the frame. It was also off-centered for me to have quick access to the micro SD card slot. Installing a 3D printer is as easy as assembling a personal computer, as they usually come with standard connectors, except for the ones that are binded to the screw terminals. With a little bit of cable management from the stepper motors, print head, and extruder, I did my best to cleanly route the wires all the way to the controller board. I made this breakout panel with a mini USB port and an XD60 connector for an external power supply. I just wanted to access these ports cleanly all in one place. Unlike in my Mark II build, I routed all the wires of the bed all the way to the top, then going down to the controller, since I have plans of adding a glass panel in the future for making this an enclosed printer. My spool holder is made from the same tubular steel I used for making the frame of the 3D printer. These are the wires for the LCD, and I did 3D print some brackets to make this work with my frame. I also printed this shaft for my favorite generic ABS filament spool. Lovely. For my LCD, I'm using the cheapest one I could find, the C-Tech Mini NeoPixel RGB LCD. Eventually, I have learned that it was not compatible with my SKR Mini, so I had to be creative and made my own cable for it. I also superglued some female headers to make an improvised 10-pin connector. By the way, here's a graphical diagram of my connections. I 3D printed an enclosure for my LCD, screwed it in place, and connected the homebrew cable to it. This one goes conveniently right in front of my 3D printer's frame. Don't forget to add the knob, then connect your cable's connectors to your controller board. It's up to you if you want to add a filament runoff sensor so that your print would pause if the filament runs out. Mine was a homebrew one I designed and used for all my past 3D printers. Initially, I wanted to use this chunky 24V 30A power supply I repaired a few years back. However, it was so big I had nowhere to mount it without ruining the minimalist aesthetics of my build. Thus, I made a quick connect IEC and XD60 shroud to turn this to a safer external power supply that will eventually power 2 other future 3D printer builds. For remote prints, as of the moment, I'm running 3 instances of Octoprint on one Raspberry Pi 4, which is why I made that quick access USB port connector. I do have plans on migrating to Clipper as I need to implement input shaping in the future. In this part of the video, I'm going to skim through on how to compile a custom Marlin config for a CoreXY 3D printer. If you're new to VS Code, please do watch this video by 3D Printscape to make your compiling work a lot easier. To make a custom Marlin firmware, simply Google Marlin firmware and head to their download page. Look for the current Marlin release and download the firmware source code and the sample config files from their GitHub page. Copy the zip files on your desktop, then extract them. You can delete the zip files afterwards. Go ahead and open the config file, go to the config folder, examples, and look for Creality. Look for Ender 3 Pro, and we'll be using that as the template. Look for SKR Mini E3 V3 and copy all those config files. Go to the main Marlin folder, look for Marlin, and paste all those files there and replace them. We can now start by opening VS Code. Go to the Files tab, click Open Folder, and look for the main Marlin folder. If you see all these folders, click Select Folder. Open the Marlin tab and click on configurationadvanced.h and configuration.h. I have provided a downloadable PDF file and checklist of the things you need to change or would probably want to change for your custom firmware. This is the tab where you can find the specific location of code, and this is what you have to copy and paste upon using the Ctrl+F function for a quick search. And this is or are the changes I did for mine. I also added some of my notes, so please do read them if you're interested. For example, to enable CoreXY to work with our CoreXY 3D printer, look for this line and uncomment it based on the notes that I have written. We also have to change some of the E-steps. For example, I'm using a 20-tooth pulley. Input 20 to the formula in my notes and you get a value of 80 for both X and Y. For my Z-axis, my ball screw actuator has a pitch of 2.5mm. Plugging in that value to the formula gives me an E-step of 640. For my extruder, 139 is provided by the manufacturer. I'm using an Ender 3 sized bed, so there's no need to change the values. For the X and Y acceleration, I do expect this CoreXY build to be able to reach 20,000 mm/s², while leaving the others untouched for now. My end stops are normally open, so I have to invert the logic. Some of my end stops are located differently from an Ender 3, so I have to specify that. The guide includes the essentials, and I will update it from time to time whenever I learn something new. Once you are ready, open the Auto Build Marlin tab and click on this Build button. If there are no red errors, a folder will appear with a successfully compiled firmware. Look for the firmware.bin file and copy it. Insert a microSD card to your computer and paste it on the main directory of the card. Unplug the SD card to your computer and you can finally insert it to your 3D printer for a fresh install of Marlin. Power on your 3D printer and wait for a few seconds.
12 seconds later.
Congratulations, you have successfully installed a custom Marlin firmware. There are a lot of things we must calibrate, but I'll be focusing on the XY skew compensation because we have no idea how badly aligned this welded steel frame is. This is the cauliflower tool and test by Vector 3D. You print this coaster, measure the edges using a caliper, and use this provided Excel calculator. My Mark III has an astonishingly low 0.17 degree skew. You simply have to just paste this to your Marlin firmware and it fixes the skew error. My Mark II build, on the other hand, had a different story. The physical alignment was relatively bad as it was skewed by 1.28 degrees. I then enabled the XY skew compensation and printed a second benchy to compare. 0.24! That is a big difference. Upon putting the before and after prints on top of each other, you'll find a noticeable difference. I can't cover all the calibration I did for this video, so here's my checklist of things to do. I did everything except for the input shaping as I am about to migrate to Clipper really soon. Before I get to the test print, here are some quality of life upgrades I did outside of the budget. I had an old webcam lying around, so I dismantled it and 3D printed this magnetic webcam bracket. It clips anywhere onto the steel frame. The view isn't pretty, but it's great for monitoring prints. The Mark II isn't using an external power supply. I was able to maintain the minimalist look by equipping it with a really dense 24V 400W LED driver. It had a noisy output, so I made an LC filter for it. I also added a PTFE guide for the spool's filament to help guide it through the runout sensor and the extruder located from behind. I also made this wooden shroud wrapped in CF wrap to make the bottom pleasing to the eye. I had some aluminum scrap, so I handcrafted the XY brackets for the Mark II using a jigsaw, a file, and my cordless drill. Back at the time I didn't have the drill press. I also added some heat sinks to the steppers to keep them a little bit cooler. It's time to show what these printers can do. With a layer height of 0.15, a travel speed of 500, a true print speed of 150 at 6K acceleration, the Mark III was quite stable. At its normal speeds, it's most definitely faster than my old printer's absolute max. Here, I subjected the benchy to the worst possible lighting conditions to highlight the imperfections. With a thin wall of 0.8mm, the hull of the boat seems to be quite good. The overhangs on the windows and holes shows that the 4010 fan is doing a decent job in cooling. The edges, however, could be better, but that's just about the limits of this Bowden extruder's setup. Also, here's a sample print of the classic wavy vase. I'm quite happy with how the initial prints came out to be for the regular speeds of this printer. But how far can we push it? Well, that's about it for the Mark III, as the V6 hot end creates a bottleneck. However, while the Mark II has the same setup, it has a 120W ceramic Volcano CHC hot end, a Triangle Labs clone for $20 that's worth every penny. With it, I was able to push the printer at even faster speeds until I've reached the limit. Without input shaping, this is the fastest it can do as of the moment. With a travel speed of 700 and a true print speed of 350 at 15K acceleration, this thing gave me so much anxiety. I pushed my printer to match the Bambulabs 12-minute 3D benchy record, and while I've hit the same time mark, the print quality didn't quite match up. In my setup, the Bowden extruder and the absence of features like input shaping, linear advance, and flow compensation were major factors. I have a long way to go if I want to match that printer. So would I recommend building a fast 3D printer from scratch? No, not unless you find enjoyment in the building process and have enough time to spare. This project was only made reasonable since I have a bunch of old 3D printing parts I have accumulated over the years. It's just another way for me to put those rotting parts to good use. So would I buy a Bambulabs? Most definitely. Perhaps in the future when I have the budget. But for now, I'm quite happy with these two printers. After all, it's a big upgrade from my old CR10. And that's about it for this project. I hope you enjoyed this video, and once again, thank you so much for watching.